Good morning. Welcome to today's session on storage, energy storage devices, day 4 of this faculty development program. Today we have Dr. Surendra Kumar Martha speaking on lead acid batteries, fundamentals, current status, and future. Let me briefly introduce the speaker today. Surendra Kumar Martha is currently working as an associate professor at the Department of Chemistry, IIT Hyderabad. He graduated in the year of 2006 from the solid state and Structural Chemistry Unit IISc, Bangalore, under the supervision of Professor A.K. Shukla. Previously, Dr. Martha worked as a postdoctoral research at Oak Ridge National Laboratory, USA, and Bar Ilan University, Israel. He joined as an associate professor at IIT Hyderabad in 2013. His recent research interests are in materials, electrochemistry with particular emphasis on advanced metal ion, dual carbon, lead acid, nickel zinc batteries, supercapacitors, and recycling lithium-ion batteries. He has over 80 publications in peer-reviewed material science and electrochemistry journals, and has over 15 patents contributed to over 75 academic conferences. So, Dr. Martha joins us with enormous experience in this direction, in this field. So I hope all the participants pay attention to what he says and learn something new in this talk. Over to you, Dr. Martha.
Thanks, thank you, Dr. Sai Santosh, for inviting me and giving me this opportunity to talk about this here and in this ATAL workshop on energy storage, on energy conversion and storage devices. So let me tell you. So I have chosen the topic. You might have heard a lot about lithium ion or other battery system. I thought let me talk about the old battery system. Lead acid batteries. Nobody talks about it actually. Many of you may be knowing it's a more than 150 years of technology. It's a very mature technology. And you may be thinking why sir is presenting this talk after 100, which is a mature technology. You'll see there are a lot of issues associated with this material. So you can pick up a topic and can do the research. It's the, and latest battery industries are available throughout India actually. Okay, and I'll tell you, there are few in this world today are working on lead acid batteries. This is very unfortunate because of the evolution of lithium and other battery system. Still, lead acid battery continues to the most successful electrochemical system ever developed, and this is a most important thing is the availability and the cost grounds. I'll talk all about it actually today. So. The goal, at any point of time, if you think, you are not able to understand, you can ask me. And after hearing my talk, you should able to, if you are really interested to do some latest battery research, you can do that actually. That's my goal to give this presentation today. And I don't know, you might have everybody uses a latest battery either in their motorcycle or car or in their inverters and so on. Correct? Everybody, almost everybody, like you use a cell phone, lithium-ion battery in your cell phone or laptop. Similarly, the latest battery is used in your home to give as a uninterruptible power. So UPS in a UPS system and other things. I'll briefly talk about it today. So let me tell I want to dedicate this today's lecture to Professor Pavlov and my supervisor, Professor Shukla, and there is a gentleman, Mr. S.A. Gapur, who gave me this opportunity to do this latest battery work during my PhD. So after Gaston Plante, who invented lead acid battery, I believe he is one of the pioneer. Desco Pavlov, who contributed significantly to lead acid batteries actually. Many of you know that this Journal of Power Sources, it was evolution of batteries mostly, and Pavlov and D.H. Rand actually. There are three eminent lead acid battery people actually, and this has become the leading electrochemistry journal today in the world. So unfortunately, this gentleman is no more. and he has significant contribution to lead-acid battery. And he visited India and gave like a series of lectures to all industry partner, industry people and academicians who were working on lead-acid batteries. We had a workshop, a week over workshop at SSU during I think 2003 or 4, and he even invited me to lead-acid battery conference. I visited over there and gave a talk when I was a student at IAC, and then followed by he visited a couple of times to IAC. I was very much attached with him, and I met a couple of times in America as well in ACS meetings and so on. And I am always thankful to Professor Shukla for introducing me to this field. I remember I was closely associated with this industry called NAD Energy Limited, and Mr. Gafur, the managing director during that time, he gave opportunity to work over there. Even after I joined as a faculty, he also gave opportunity to work over there. Anytime our students can go and can do the research and get things done from the industry and develop the batteries and bring to the IIT Hyderabad do studies. So we can really from the scratch we can develop lead-acid batteries, commercial graded lead-acid batteries. I remember during my PhD, I have developed 100 ampere hour, even 200 ampere hour. This is 2-volt cells, not only 2-volt cells, 12-volt cells, and a couple of my technologies have been commercialized by NAD Energy Limited, my PhD work. So, you will see many things in the lead-acid battery today. So before going to today's presentation, let me say about our group. And we mostly work on the new materials, study their electrochemical interfacial properties, designing new electrodes and electrolytes, basically for the lithium ion, sodium ion, potassium ion batteries. Even recently we have started dual carbon batteries. We also do a lot of work on lead-acid battery system, like not only lead-acid batteries, we have extended to lead carbon batteries and ultra batteries. That's I am going to show today. Also, we work on supercapacitor and recycling lithium ion batteries. Unfortunately, in India, we don't have lithium ion battery, manufacturing industries. They get all cells and manufacture, not from the scratch, material development to the cell. Still, we still don't have don't have tie up with the good industries. We are trying actually. So in my lecture, you will see that I'll give a brief introduction to lead-acid batteries, the fundamentals. You will see I'll be talking about how we can prepare electrodes, how we can assemble them, test them, what are the failure modes. Maybe initially I'll speak the failure modes, and how we can address these failures by various concepts like lead, this carbon additives, lead carbon capacitor, ultra batteries, and then I'll briefly summarize the talk. So, as all of you know that energy is a peculiar entity, the lifeblood of modern society, correct? The access to energy is critical for the wealth, lifestyle, and image of every country. So, you always think if you don't have access to energy, you are not a developed country then. So if you look at India's energy balance, we are still lacking a lot. And even in the world, it is almost identical, like whatever is produced today and is consumed. But that scenario is going to change in the next decade. Completely the scenario is going to change because of evolution of renewable energy sources. Correct. So we expect the fundamental breakthrough in clean energy research is needed to solve the problem of such high magnitude. Okay. So if you look at the energy environment, we have oil, natural gas, coal, nuclear, and many renewables and so on. So in India, we use mostly coal, bio waste, gas, the hydro, and renewables. Correct. And you might have listened to Professor Bijamon, he was telling by 2022, Indian government plans to have 225 gigawatt of energy from the renewable, from the like wind and solar, and they were achieving. I don't know the updates in last 1 year, so they were up to the mark in the renewable sector actually. So this is going to change the scenario of the energy sector actually. And so if you look at the energy, renewable energy sources, as already I told you, we are using solar, biomass, hydrothermal, geothermal, and so on. Correct? Sorry. But the issue associated with this renewable energy sources that they are intermittent in nature. So we need to store them for variety of application. So when it comes to storage comes into the picture, we have batteries, fuel cells, supercapacitors, correct? So battery, you find I don't know how many of you have seen supercapacitor or fuel cells. But all of you have seen batteries. Batteries are available today everywhere, and the battery, latest battery have been emerged from 1950 itself. It was available. And Plante, even he made in the 1870 or 80 when latest batteries, and he I don't know to Napoleon Bonaparte he showed a lighting up a city with the latest batteries. So this I'm telling late 1900th century there, and so the batteries are available today, and they are cheap, not very expensive compared to the other systems actually. So if you see the energy and power density, we might have already know about energy density and power density. So in a crude way, I generally tell it's like your Panther has a high power, or Usain Bolt has very high power. He can run very very fast in 100 meter in 9 seconds. So that means he has high power. And when you talk about energy, so like how fast you drive your vehicle, another way. Okay, when you talk about energy density, like how long you can ride, like a camel, can walk throughout the day, correct? So it has a high energy. Okay, so fuel cells have a high energy, whereas capacitors have a low energy. Capacitors are the pure capacitors, ultra capacitor. They have energy of less than 7 watt-hour per kilogram. And now we have pseudo capacitor and all. So there we can reach maybe 25 watt-hour per kilogram. Okay, so among all the batteries, so there are several batteries. So mostly you might have been using lithium-ion batteries, lead-acid battery in your home. And if you have old gadgets like cameras and all things, earlier the old cameras, they use the AA, AAA, like rechargeable cells. And even your the mouse, it is just a AAA cell or and so on. See there, if they are rechargeable, they are nickel-based batteries. So we know few uncounted batteries. So lithium-ion batteries have the energy density of about 150 to 200. Sorry, now it's more than 200 watt-hour per kilogram, but it's like 150 to 250 watt-hour per kilogram. Whereas the lead-acid battery, with the energy density very very poor. This is just 30 to 40 watt-hour per kilogram because lead is heavy. I'll come to that actually. So before going to today's the cells and batteries, I just wanted to give you a flavor of how you make electrochemical cells. Basically, you all have seen electrochemical series, standard electrochemical series. You see these are the strong oxidizing element, these are strong reducing element, right? So if you can combine lithium with chlorine, you can get a system of 6 volt, around 6 volt. Even you have recently krypton fluoride, krypton fluoride to krypton. If I remember, krypton fluoride to krypton, it can give 3.27 volt. And praseodymium, it can give not praseodymium, strontium. Strontium can give 4.01. Strontium plus to strontium can give you 4.14. See the systems. See, you can get a system of close to 7.5 volt system. But unfortunately, you don't have electrolytes operating at such high potentials. And so on. Or the material stability is another crucial factor. So by combining, the strong oxidizing element and strong reducing agent element, you can get an electrochemical cell. And by this way, if you have 100 elements in the periodic table, you can get 100 C2 electrochemical cells. That means at least 100. That means around 4,950 electrochemical cells. But in real, if you see, you have tens of electrochemical cells. Like as I told you, lithium ion, sodium ion, potassium ion, or your lead acid, nickel based, or silver zinc, or zinc ion. Few battery systems exist today. Okay, either the material is not stable in the electrolyte, or their stability issue. Many factors contribute to it. Okay, so you have a cathode and anode. So now when you complete the circuit and you have electrolyte, when you complete the circuit, so like electron flow from the anode to cathode, like you have high potential energy to low potential energy, up the hill to the down the hill. So electrons flow from the from the anode to cathode, and you have flow of anions. So and cations, so we see the oxidation and reduction at the anode and cathode, and that brings the voltage to the cell. In the latest cell, if you assemble, even in the, if you have a, see, I have a cathode, I have an anode. So in basically you have this is the anode, this is the cathode here, what you see here, and in between I put a separator which separate between the cathode and anode. Okay, I put a separator which separates between the cathode and anode, and then I put into the electrochemical cell. Okay, then I connect the load, and then when I do the charge discharge, so when you do the oxidation reduction reaction, that brings voltage to the cell. Okay, so this is how the electrochemical cell works. So another important thing I want to tell you how to calculate the specific capacity. Okay, so you all know about Faraday's law of electrolysis, correct? The quantity of electricity equals to 1 amp in 1 second. That means 1 ampere hour equals to 3,600 coulombs. So all of you know that 1 gram equivalent of material delivers 96,500 coulombs. Okay, 1 gram equivalent material delivers for 96,500 coulombs. That means 96,500 divided by 3,600, you get a 26.88. That means 1 gram equivalent of lithium can deliver this much capacity. 1 gram equivalent of aluminum can deliver this much capacity. 1 gram equivalent of sodium can deliver this capacity. 1 gram equivalent of lead can deliver this capacity. So I'm talking a term, you see it not a gram, it's gram equivalent. Okay, so gram equivalent of lithium is 6.94. Gram equivalent of magnesium is 24 divided by 2 is 12. Gram equivalent of aluminum is 9. So if you calculate accordingly, you see 1 gram of lithium can deliver capacity around 3,860 milliampere per gram. Or 1 gram equivalent, 1 gram of aluminum can deliver about, I think, 2,977. This is aluminum, 77 milliampere per gram. This is how we calculate actually. So any element, see, suppose somebody gave you a material, my friend, can you check? First, we need to know what is their like oxidation reduction potential. Then another important thing is what is the capacity? Okay, how much capacity? First, we see how much capacity it can deliver. You give me a carbon material, I just see how much capacity it can deliver. So I calculate, for graphite in the lithium ion cell, it can deliver about 372 milliampere per gram. Okay, so specific capacity I can write in terms of like 26.8 divided by molecular weight into the number of electron transport during electrochemical process. In basically, this is theoretically. In real, in practical. So you don't get all the lithium or all the lead, like 1 electron transfer or 2 electron transfer or 3 electron transfer in case of aluminum. So the amount of electron transport into 26.8 divided by the molecular weight will give you specific capacity. This is how we calculate. So now I hope you understand how you choose the electrodes, how you calculate the capacity, you got the voltage, and now let's talk about a little bit about lead acid battery, the capacity and energy. So in lead acid battery, lead is used as a negative electrode, lead dioxide as positive electrode, and sulfuric acid as electrolyte. Okay, this is, I'll come again. This is the negative electrode, this is the positive electrode, this is the sulfuric acid electrolyte, and you get around 2.1 volt actually, 2.1, 2.15 volt in open circuit condition. If you calculate 1 gram equivalent of lead is 207 gram per mole. 1 gram equivalent of lead dioxide is 239.2 gram per mole. 1 gram equivalent of sulfuric acid is so this is a 2 gram equivalent. So 1 gram equivalent will be around 98 gram per mole. Okay, so that means so you can easily calculate the specific capacity. You see, just now I was talking, see, lithium is 3,860, and you see here you have a 260 milliampere per gram. 1 gram of lead can give 260. In real, maybe we have developed better active materials. It can give you around 100 milliampere per gram or 120 milliampere per gram. Okay, and then you calculate the specific so capacity 1 by x plus 1 by y plus 1 by z. So many people don't consider sulfuric acid, and in lithium ion cell we don't consider the electrolyte. Actually we consider only cathodes and anodes, and we calculate the capacity, the specific capacity, or the cathode itself if it's a half cell. Okay, so here it's both. So sulfuric acid take part in the electrochemical reaction, so we consider this, and if you don't consider, so you get a different number, and I'll tell you that. So you got the specific capacity, which is 0.08 ampere per gram. If you multiply it with the voltage, that's your energy. Capacity into the voltage is your energy. If it is the voltage is 2.1 volt, you get 168 watt per day. You get 168 per watt hour per kilogram. If you eliminate H2SO4, you get 240 watt hour per kilogram. 240 watt hour per kilogram, but in practically it's a 30 to 40 watt hour per kilogram. Very strange. This is because lead is heavy. And another important thing, I'll come to that actually. Although you see this is a casing. Many of the things, there is a separator, there is a current collector. All these components are not used for the electrochemical reaction and efficiency of the material. And then many other factors that contribute to this capacity. We'll talk all about today. Okay, so in similar way, if you calculate, already I told you lithium. If you calculate lithium iron phosphate, which is a cathode for the lithium ion cell, you see it has an energy of 560 watt hour per kilogram. Lithium cobalt oxide 520. Lithium manganese phosphate, you get 615 watt hour per kilogram. There is a lithium manganese rich NMC is 1036 watt hour per kilogram. You can see, if you are interested, you can see to my profile, you can download these papers, or you can ask me, I'll send you the papers. So in lithium ion, so lead acid, you have 30 to 40 watt hour per kilogram, whereas lithium ion, you have around 200 watt hour per kilogram. Okay, so if you look at the, let's say, batteries. So battery was developed in 1800th century by Alessandro Volta. He used copper and zinc plates, copper, zinc, and in between a brine cloth solution. Okay, brine was the electrolyte, cloth was the separator, and he used to get 0.76 volt for the cell. Okay, so and today you see he used copper zinc plates, stack alternative to get to get the batteries. Now today, even after 100 to 200 years, we use the same concept of making batteries. This is a stack which is used in electric vehicle by Chevy Bolt, your General Motors Chevrolet Bolt, and this is around 200 kilogram of battery, 16 kilowatt hour battery stack, which is around 200 kilogram. It also uses the combination of like a series and parallel to get the voltage and the capacity. So to increase the voltage, you will need to combine them in series. To get capacity, you get combine them in parallel. Okay, so this is how the even today we use the same concept. So let's come to latest batteries. Right. So now you understood how I can design my electrodes. Okay, how I can get my cathode, how can I get my anode, and then I didn't talk a little bit much about electrolyte. See, when you are using water-based electrolyte, water decomposition potential is 1.23 volt. So the operating voltage will be around that voltage. If you want to go see lithium-ion battery, can you use aqueous electrolyte? No, there are a lot of issues in this. So first, the voltage, water decomposition potential is self 1.23. So if you are going beyond 1.23, that means you have a hydrogen evolution and oxygen evolution occurring inside the cell. That's the one important thing. And if you go to high voltage, you need to have organic electrolytes. Once you go to your organic electrolyte, your conductivity significantly reduces 1,000 times. Okay. Similarly, if you go from the non-aqueous liquid electrolyte to the polymer electrolyte and solid electrolyte, then conductivity significantly reduces. That means the ionic mobility, the mobility of the electrolyte, the ions reduces, the conductivity reduces. That means when conductivity reduces, you cannot do the fast charge discharge. Okay, so in lead-acid battery, as I told you, so lead-acid battery was invented by Raymond Gaston Plantin in 1859. And you can see you can be available in the lab. I can make this is a 4 ampere hour cell. If it is a 7 into 5, it is like a 3 to 4 ampere hour cell actually. Okay, if you can see, I said like it may weigh about maybe 50 gram. This is the same. I have a lithium ion cell. You see, it may be 5 gram, and you can see it is a. I don't know whether you can see clearly. If it is 3.7 and 200 million, 2000 million, 2 ampere hour. The weight is maybe kind of 10 times lesser than the lithium ion cell, the lead acid cell. So but still, if you see in the latest itself, they are, I'll come to the next slide. They are cheap, abundant, availability, and completely recycled. And the latest battery also you can get from 1 volt, 2 volt till 1000 volt of system in our company itself. They develop. These are the 12 volt system. They have also 2 volt, 200 ampere hour systems to 2 volt, 1000 ampere hour or the systems. And then if you see their performance is around 1000 to 1500 cycles. I'll come to that actually. And then if you see the market share is around even close to 30-50% of all the batteries in the world actually. Still latest battery occupies like close to half of the market share, like 40 approximately 40% of sales value of all the batteries in the world. And you can see the latest battery, you come out to your house, you will see a latest battery showroom, right? You may not see. I got a lot of lithium ion cells recently for some work. So this is actually open from a special vendor. It's not available everywhere. Even electronic shop you go, you may not get. He will tell, give me a day, I'll get it. She has to go through it's not available everywhere. Whereas, the latest batteries is available everywhere. Every street you will find a shop. You will find Exide showroom, inside Amaran showroom. You have a multi-company showroom as well. So you have a lot of variety of latest batteries available today in the market. If you look at the cost is a 50 kilo. This is a per kilowatt hour. It is 50 euro. Whereas, sorry. Yes. And for lithium ion is around 100. At the present, it's around 100, 125. So the people are trying to reduce. And if you see recyclability, latest battery is 90-80% recyclable. We have a industry partner called Nile Limited. They have factories at Hyderabad and Tirupati. They recycle the batteries. Latest batteries completely. The container itself, so that can be completely recycled. The electrodes can be completely recycled. The separator can be completely recycled, and so on. And available the material is available. It has, but not compared to cycle life. Cycle life is much lesser in lead acid cell compared to lithium ion. And safety, if you see, now it's a BRL. It comes with a valve regulated design. It is much safer. It's very, very safe. And there is no electrolyte spillage even. And it can work even minus 20 degrees centigrade. That's what military people have been using, latest batteries. Okay, so it's available everywhere in the world even. So any like readily available, recyclable. If you look at the application, you see, latest battery can be, I told you, wind power, solar, you can telecommunication, you have, portable, your bikes, e-bikes, everywhere, you can use this inverters, this, you can see, this is solar, and even your vehicles. All the vehicles, two-wheelers and four-wheelers have a latest battery. Even though I'll tell you, even you have a complete EV, you will have also latest battery for SLI application. For starting light ignition, you will have a latest battery, right? And even now you see there are many vehicles comes with this called a smart hybrid. What does that smart hybrid? It is like what it does actually. This is basically start-stop application. When you are in the traffic, correct? When in the traffic, the engine is stopped. The battery is working now. The battery will be discharged. When the engine is cracked, so when you are starting again engine is cracking, the battery is getting discharged, correct? And when in the driving phase, the battery is getting charged. And this is the latest battery mostly used in the vehicles today, start to stop application. So that saves a lot of fuel, the fuel efficiency is increased. So SLI start-stop application still, Professor Bijay Mohan was telling Reba was imported 1 million of vehicles were imported to Europe, so about 5 years before. I have seen Reba during my PhD days. I have visited Reba, currently is taken by Mahindra. They used to get maybe chassis from imported from abroad and batteries from India, and then they used to make the EV section. Even now auto rickshaws and all, even many places you will see also this latest batteries. Latest batteries. The advantage is that you don't need a special cooling system. Thermal stability is high. They have moderate life. When there is no space limitation, lead-acid battery can be used. It's cheap, available. Even if you have factory, you can recycle completely, and that's why it's most advantageous than other battery systems. So and our like still we talk even Amaraja, HBL or Exide, they are doing on lithium-ion batteries. So but still they cannot leave all the things because this is one of the key business for them actually. This is has been significantly used by the users. This is one of the like bread and butter for the company. See, Exide may have tens of companies in India, manufacturing facilities in India. See that much business they have. Okay, so electric vehicle is one of the important area. Still, now the lithium-ion battery and supercapacitor may occupy the landscape, but still lead-acid battery will remain. Will be used for SLI application in the electric vehicles as well. So by our Transportation Ministry has announced 30% EVs on the road by 2030. So that means that's why you will find a lot of lithium battery manufacturing companies in the future as well. And we have also a EV program in IIT Hyderabad, and so we demonstrated a solar operated auto with this Japanese venture. Unfortunately, and this is supported by JICA and Telangana government, but unfortunately, these two people are very old, above 75, because of current pandemic. They cannot travel, and our the activities are almost stopped. So maybe I believe it will resume very soon. We are trying to demonstrate basically high temperature lithium-ion batteries for Indian condition. India condition, you can go from 0 degree or -10, -20, the Himalaya region to 55 degrees centigrade. Indian condition is different than any other climatic condition. So how in Indian condition we can make a good, better batteries actually. So with this, I'll go with now latest batteries. So already I told you lead is as a negative electrode, lead oxide as positive electrode, sulfuric acid as electrolyte, and you can see here during so basically in the when you get the material, it's lead sulfate. When you charge it, you will form a lead dioxide at positive and lead at the negative electrode, and then you see here while charging. So you see. Another important thing, you'll see that water. So oxygen evolution takes place at the positive electrode and the hydrogen evolution takes place at the negative electrode. And you see the voltage is 1.7 volt in the cathode and minus 0.36 volt at the anode. So that means around 0.47 volt above the decomposition potential of water, and minus 0.36 volt than this for the hydrogen evolution. So you can see here that means the oxygen and hydrogen always evolve from the lead acid battery, even in the standby condition. But the extent of oxygen and hydrogen evolution may happen when you go for the charging, high voltage charging. Okay, so you can see here. So in a cell, you get a 2 volt, and in your home you have a battery which is consists of 6 cells. They are combined in series to get a 12 volt. And basically, in the charge condition, it is around 13.2 to 13.5 volt actually. And basically, it is a charge in that region. Always, it is a full charge condition like 13.5, but it can go. See, we'll discuss all about today. So already I told you oxygen evolution at the positive electrode and hydrogen evolution happens at the negative electrode. And if it is a flooded system, if it is only free electrolyte like your inverter system, so these gases can escape, and then you may have change in concentration of electrolyte. That's why maintenance is required. Topping of water is required in latest battery. So periodically, that's why you are keep on adding water to maintain the level on the top of the plate, so that your concentration of the electrolyte, it doesn't change. If concentration changes, suppose the level of water reduces to half, that means the concentration significantly changes. That means if it is very high concentration, then there will be a lot of sulfate formation. As you see here, once the lead sulfate is formed at the positive and negative electrode, it stops the charge. The charges cannot enter into the bulk of the electrodes actually. Okay, that stops the electrochemical reaction. So, how to reduce lead sulfate reduction? That's what we'll talk today even. So, if you see a latest battery, you have I have commercial grades. So you see here, I have a grade which is this is the current collector. This is purely made up of lead. It's very heavy actually. Okay, the active materials are coated onto it. And you see what is the active material? You see here, these are the active material already coated onto this grids actually. Okay, so that delivers the capacity, not this thing. Here only current passes. This current. And if you see the same for the lithium, you can see here, this is the current collector and the activator, the black section is the activator of the anode. And you can see here, this is basically a copper coil current collector. This is for the aluminum. So you can see here, this is the cap, and this is, you see, if the weight is around 150 gram, and here it will be 2 gram or 3 gram, the cathode itself actually, cathode and anode. Very light, even less than that actually. The weight is significantly less in the lithium ion cell actually. So this is very light, and this, if you see here, this is around 20 micron aluminum foil, and around 100 micron is coated. Whereas the lead acid, the grid itself is around 3.4 millimeter or 3.5 millimeter here actually. The thickness of the grid is around 3.5 millimeter, and the lead active materials are coated onto it. Okay, I'll discuss all about it actually. In between, we put a separator. It can be objective glass mat or a polymeric separator. I just show you in a minute. You can see here, this is called objective glass mat. You see, this is objective glass mat. Okay, this glass mat, this absorbs lot of amount of electrolyte actually. This is used in a VRLA battery called valve regulated lead acid battery. I'll come to that actually. So this is the separator. In general, people use, you can see here, there is either PVC separators, polyvinyl chloride separators can be used, or even polyethylene separators can be used as well. Okay, so this is the grid. Then you have a positive electrode. That's why I showed you the negative electrode, and then you see we put separator, and then we put in between the cathode and anode. So to increase the capacity, so what they do actually, so in one cell, you see all the negatives to increase the capacity. See, one electrode may be 10 ampere hour. To suppose in your 65 ampere hour level cell in your battery, so you see here 1, 2, 3, 4, 5, 6, 7. This may be 100 then ampere hour. So around 9 are there. That means one will be giving around 12 ampere hour if you combine them, you will get 100 ampere hour. Okay, and similarly, see, generally we take positive limited cells. That means that the capacity of positive electrode is lesser than the negative electrode. So why is that? Because as I told you, maybe I'll come to that. The oxygen which evolves at the positive electrode, we want to combine at the negative electrode. That's I'll come to that in a very version. So and then so these are the you see, this is the positive stack, this is the negative stack, and then you then in between you join together and put into the cell. Okay, so you put into the cell actually. Yeah, so you put into the cell and then you seal in the industry you seal them, and then so you fill the electrolyte, then you seal them. Okay, so to get voltage, I just told you, you have to connect them in series. To get the capacity, you put them in parallel. Correct? Already I told you actually. Okay, some cases also people use this kind of this is a polyethylene separator actually, polyethylene separator. Okay, you can get even in the back type as well. And there are a lot of industries they can make for you these separators. And this polymer industries there are thousands of polymer industries in the country. Every place you can find tens of polymer industries actually. Okay, so you see, so this is 1, 2, 3, 4, 5, 6. So 6 compartment, 6 into 2, you'll get minimum 12 volt. In the full charge condition, you'll get 13.5. You use aqueous sulfuric acid. Generally, 4.5 molar sulfuric acid is used. 4.5 molar sulfuric acid is used to make and this put onto the top of then the cover is put and sealed. Okay, so if you see in real, we have 3 kinds of lead acid batteries. Flooded lead acid battery, where the electrolyte is free. It is put on the top of this thing, and always this kind of whatever you have in your home, that is a flooded. Maybe if you have a BRLA, you can use in any orientation. When it is flooded, if you are adding water, then you cannot use them in any orientation. It has to be placed in the always in upright position. Okay, another, so they have to be vented also. So that's why the oxygen and hydrogen evolves during charging, that escapes, and you have electrolyte changes, electrolyte concentration changes. That's why you are topping with water. And the problem is that, see, if it is a closed room, you have a kind of corrosive sulfuric acid mist, which is evolving from the battery always. It's not good actually. Okay, so when you keep a flooded lead acid battery, you should keep in an isolated position. And the other one I told you, the valve regulated lead acid battery, same. So this was evolved during 1970s. So in valve regulated lead acid battery, so they use a separator called absorptive glass mat, or there is another valve regulated called gel. They use a gel electrolyte. What is gel electrolyte? So this is made up of silica. Okay, so this is a very good separator. It can soak a lot of amount of electrolyte. It is a more than 70% porous. So the main advantage is that you see here, the oxygen which evolved at the positive electrode will go through the pores of this and combine at the negative electrode. So what will happen? So Pp reacts with the oxygen to form PbO at the negative electrode, and you have sulfuric acid. So you can have a kind of cell discharge reaction. But this is a discharge product. As the cell is under charge, this is an advantage, but this is in lead sulfate formation is a disadvantage. But as the cell is under charge, lead sulfate is get converted to lead, and that's why. So what it will do actually, once it combined on the negative electrode, so oxygen doesn't escape. So it increases the hydrogen evolution potential actually. It reduces the hydrogen evolution. And suppose, this generally happen more around 2.25 to 2.3 volt in a lead cell. And generally oxygen evolution starts around 2.4. If you don't have oxygen recombination, it increases to 2.45. You see in your home, the battery is charged only 2.3 volt per cell. So you don't go to this one. For some commercial application, if you are going to 2.4 volt, then this hydrogen evolution can be eliminated. So this is based on oxygen recombination mechanism. Valve regulated lead acid battery. There is a valve also there. that will automatically opens in the but if you add water, it is not going to absorb anymore, maybe little in the top. It's not going to soak much of this water. So topping of water is not required for the BRL system. It's completely maintenance free. It is you can go for deep discharge. That means you can go to zero discharge, like completely drain out all the capacity, and you can use any orientation. But the life is shorter. Here it is more. If it is 5 years, here can be 2 to 3 years actually. The life is somewhat shorter, and in the so this is what already I told you about gel. This the advantage that also the AGM has a low internal distance. It can deliver high currents, and so they can offer go long cycle life, but life is around 3 years, and it's completely maintenance free. They are less prone to sulfation, but it depends on the application. I should not tell that. This depends on the application, and they have a little bit less self discharge because of oxygen decomposition and followed by charging. And water retention is so you don't have to add water throughout the life, so it's completely maintenance free. And the other one is gel. So it's similar to AGM. You put a separator like flooded battery, then you mix a fume silica with sulfuric acid. Same 4.5 molar or 5 molar sulfuric acid, you mix with silica, you make a gel. So this I patented what my PhD work for this, and then it is utilized by Energy Energy Limited. They make, I think they are the only in the country who makes the gel. I don't know anybody else makes. So they are they make a lot of gel electrolyte BRL batteries. So what happens? So when you put the gel, so after some time you will have cracks. Through the cracks, the oxygen goes and combine at the negative electron. The gel is somewhat cheaper. This is a little bit expensive, but nevertheless, so both works very well. Yeah, so they have different application. Even though they look very similar, they are designed for different application. So in real, if you see, if it is 100% charge, that means the state of charge is 100%. What do you mean by state of charge? Is the capacity at any instant to the total available capacity. The capacity at any instant to the total available capacity is called state of charge. Okay, so that means when it is 100% state of charge, the depth of discharge is 0%. The electrolyte concentration is around 5 molar, and you see that is means 1.26 to 280. And then the load voltage, after the load voltage around 2.7, at least 2.1 volt per cell. Okay, the load voltage. So it is a fully charged. And when it is complete discharge, you see there is a significant change in the concentration. Okay, this doesn't happen in the lithium-ion cell. Okay, and so this is the in the aqueous systems. This is the one of the concentration changes during the charge and discharge, because water is getting formed during discharge. So the concentration of sulfuric acid changes to 2 molar. Again, during charge, it go back to the 5 molar. So complete discharge means you have 0% capacity, and the depth of discharge is 100%, and electrolyte specific gravity is 1.1 molar, and then the full discharge voltage, it can be 10.5 to 11.7. So it's almost like a 1.7.5 to 1.9 volts per cell. If you have any questions, I can take a question at this point. Okay, if no more questions, let's go ahead. As I told you, so how we can get the potential of this latest cell? You already know that the concentration changes if you know the concentration of the sulfuric acid. So you know the standard electric potential by Nernst equation equals to E naught, which is 2.047 RT by F ln of activity of sulfuric acid to water. So if you know, you can get easily the EMF. A very simple derivation has been obtained from for the lead acid cell. So B, the EMF equals to 0.84 plus acid specific gravity. Okay, if it is a flooded cell, you can easily determine what could be the voltage of the cell by knowing the specific gravity. Suppose you don't have multimeter, you know the specific gravity, or if you know the EMF, you will know the specific gravity of the cell. This is 100% accurate, more than 99% accurate actually. So this is called 84 factor. So if you know the specific gravity, then you can easily go get the voltage, or if you know the voltage, you can get easily the specific gravity of the electrolyte. Another important thing is that the capacity. Capacity, as I already told you, is the charge, is the current into time. So if sees the capacity, the current, discharges in a battery in 1 hour. So sees the capacity, and I is the current, and T the time. So we can write capacity equals to Cp equals to I to the power Nt. This is called Picard law. I'll come to that. In general, for a lithium-ion cell, maybe if 1 ampere hour level cell, that means if it is one C rate. 1 C rate is the capacity in 1 hour. That means you are passing 1 amp current, and C by 10 means you may be passing 0.1 amp current. Correct? 5 C rate, so 5 times of this. But in lead acid cell, it doesn't follow the same trend. Most importantly, it doesn't follow the same trend. So what we do actually, we determine 1C capacity. So we determine 1C capacity, then some other and the current, basically. So if you plot, you see log C versus log T, log I, correct? Sorry. Okay, log T versus log I, if you do, so you will get a straight line. So suppose you have the current for the. Okay, so this is how we calculate capacity. So capacity in capacity nothing but I call the time into the current. Correct? This is in ampere hour. We generally make in lithium ion we make a very small tiny cells. That's what we tell in milliampere hour. Here we make at least this is this is one level of cell we make in the lab actually. Okay, this is very small. At least 7 to 5 centimeters. This is 35 centimeters square area. Whereas in the lab we make a mostly coin type cell of 1 centimeter square area. I just show you. I believe you can see here, we have a lot of coin type cells. So this is basically in the lab scale we use, whereas the lead acid we use in bigger cells. We always define in ampere hour. So this is the Picard. By using Picard plot, this is my own data during PhD, 2 volt 200 ampere hour hybrid VRL cell. This is a AGM and gel hybrid. That's how we make in NAD energy. So the Picard equation, by using Picard law, we calculated the current and current at a particular C rate. So this is the point I sense I saw. I hope many of you may be knowing. So the main issue in the lead acid cell are, I'll tell you, whatever you see here, the materials are not utilized for electrochemical reaction on this. Is the efficiency is 40-50%, basically. Efficiency is 40-50%. And it takes minimum 3 charge discharge cycles to get full capacity. So initially itself, if it is giving 1 ampere hour, you are passing 0.1 amp and it's supposed to finish in 10 hours. But lead acid battery first cycle itself will take 48 hours. Then again, so you may get 70% efficiency. Then the second cycle, you may get 90% efficiency. Then third cycle, you may get a 98 or 99% efficiency. So minimum 3 cycles is required for the formation. So, we have developed the processes where you can do the formation in 1 cycle. Okay, so that's very, very important. This is one important area, the low utilization of active material. How we can improve the utilization of active material? Another important thing is the corrosion. See, the grids are very thick. This is because, so there are many issues. So one is the positive grid corrosion. So what is grid corrosion? In both the positive negative, we use this lead grids. This is based on the lead, calcium, tin, aluminum alloy. I'll come to that. And so in the both positive and negative, we use lead. But remember, at the positive, lead dioxide is the active material. So that means when you are coating PbO2, you form a PbO2. That means Pb and PbO2 doesn't exist together for thermodynamic region. If it exists, then it will be voltage will be zero, right? So there exists an intermediate layer called PbO layer between the grid and the active material. Okay, so there exists a intermediate layer. Okay, that called grid corrosion. Okay, if this layer comes into contact with acid, then it will form PbSO4. Then it will lose. Then the issues will start. Then the current may not pass, and then you may have joule heating and other issues. We'll talk about. So part one is the low utilization of active material. Second one is grid corrosion. Third one is, already that hydrogen and oxygen evolution can cause together water loss. Even hydrogen evolution and grid corrosion can cause, hydrogen evolution and grid corrosion, what I talked in the last slide, can together cause the water loss even. You can have even water loss because of these two reactions. Another important thing is that if you leave the battery, in a charge condition or discharge condition, you have still self-discharge. Okay, that means so you have, because as I told you, what you are using water-based electrolyte, aqueous sulfuric acid, which is 4.5 polar. Oxygen evolution and hydrogen evolution always takes place. So oxygen combined with lead to form PbO, and PbO reacts with sulfuric acid to form PbSO4. This is the discharge product. So PbSO4 is formed. That means you will have, you see around 10 to 15% per month in a lead-acid cell, even more in some cases. So this is one area where you can even work. I'll come to that actually. Already I told you about this slide. Because of lead is heavy, you see, versus lithium is 6.9 gram per mole. You use aluminum foil, copper foil, they are very, very thin, lightweight. You use 20 micron of or 15 micron of aluminum foil. Okay, that's what I showed you. Or 12 micron of copper foil. Even now 8 micron is used. Very thin current collectors. Okay, that's enough for the lithium ion cell. Whereas we cannot use them in the sulfuric acid environment. So we have to use lead grade. Lead is heavy, and I told you lead weight is 207 gram per mole, whereas lead oxide is 239 gram per mole. It's very, very heavy. So if you calculate the energy density, it's the practical realized energy density in the plotted cell is around 25 to 30, and in the VRL cell is around 30 to 40 watt per kilogram. It's very, very less because it's heavy. In the past, we tried to make even lightweight VRL cells. I'll come to that actually. So I have put here actually. Instead of in the end, I wanted to tell you here itself if I miss it. Simply see, lead grade is around 50% weight, and this is only for current collector. It doesn't give capacity. Add extra weight to the battery. You can think of, can I develop some lead grade which is stable in sulfuric acid and has less corrosion, and then I can use for I should reduce the weight. Even you can reduce significantly. In the past, if you see, I have done during my PhD many of such kind of work where we used plastic grade as the best substrate. We coated with a thin layer of copper to make conducting. That is the electrolyzed copper plating with the help of Titan industry. Then we do the lead coating. We have to have lead, correct? Because copper again will form this will copper sulfate once you use in the electrolyte, and then conductivity will be lost. We use lead coating. Lead again goes to undergo for corrosion. We made a corrosion protection layer, and it was we were not, we were very close to successful, but we could not commercialize it. Actually, it was a big project during that time for EVs. So in this way, you can gain 35% of weight. The energy density can increase to 50 watt-hour per kilogram. This is still quite good actually. So you can think in this direction to do a lot of work. So low utilization of active material, the water loss, the grid corrosion, the weight loss reduction, and then there are many other issues like the sulfation at the negative plate. So lead battery, the sulfation is always formed at the negative plate. The negative plate sulfation is one of the major issues in lead acid battery. So once lead sulfate is formed at the negative plate, it doesn't allow the electrons to flow and ions to move, and the battery stops immediately. And already I told you electrolyte loss. If it is a high temperature, there is a possibility of loss of electrolyte at high temperature more actually in a non-sealed battery like flooded batteries. Stratification, that means if it is a tall battery, the concentration at the top and bottom will be different. The stratification will also make a problem. So that's why people many times, if it is a tall battery, they put in the horizontal instead of vertical, they put a horizontal position, so that the stratification will be reduced. You can not do steering or to reduce the stratification. But so this, like how to reduce stratification? The concentration should not change. If concentration is very high at the bottom, then what will happen? You will have more lead sulfate formation. More lead sulfate formation will cause significant capacity loss. And in some cases, separator failure is very less in general. And then always we should keep in the fully charged condition, not discharge condition. Discharge condition will lead to lead sulfate. Lead sulfate formation is the biggest problem in lead acid battery. How to reduce lead sulfate formation? These are the important areas you can work, for the lead acid battery. So again, in summary, I just want to tell you, oxygen evolution always takes place at the positive electrode, and oxygen reduction at the negative electrode in the vehicle cell. Hydrogen evolution at the negative plate, oxygen reduction is at the negative plate, grid corrosion at the positive plate. We tell plate because it's very, very big, and water loss because of hydrogen evolution and grid corrosion together cause water loss. Sulfation always happen in the both electrodes, but a negative electrode is more, and the self discharge also again is a lead sulfate because of lead sulfate. And specific energy is very, very less. You can, these are the areas you can always work. I'll come to this area in the later slides actually. Any questions at this point, my friends? Okay, so let's talk about how we can now we understood the theoretical aspects. What are the issues associated with the lead acid battery and how it works? And now let's see how we can make them in the laboratory. Okay, so you can get, so first I told you this is the grid. You have grid, you have separator, you have you see that you have different design for positive and negative event to reduce corrosion actually. And you see this is the negative grid, this is the positive grid event. The different design people do. And even for current distribution, you can see here the current, the grid here, you see here, very nicely designed. This is another design. There are like, see current passing from here to all over here. You can see here, 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 like this. Instead of they have a spine here in another way. Current can pass like this, current can pass like this, current pass like this, and so on. The design is different here, and the design is different here. So this is also another way, like how to improve the active material utilization by developing different design of the grid set. Okay, so anyway, these are the grids, then these are the electrodes, and I showed you separator, and you put them in a stack in the battery, and then there. So let's talk about let me skip this one actually. So I'll come to this one later. So what are the technology of preparation? Maybe so first we need to prepare the paste. For this paste, to quote on this thing, we have to prepare the active material paste, the paste. So you see here we have different components like lead dioxide, water, sulfuric acid, carbon, and so on. Like I'll discuss all the things in the latter. So you take all this active material, mix them, make a paste, and coat onto the grid. Then you dry it. Then you do a curing, and then you prepare the electrodes. Then the electrodes once ready, then you can analyze them. Okay. So first is the grid. Okay. The grid is basically the lead, calcium, tin, aluminum alloy. So you see, more than 90-80% is lead, and a little bit of tin, calcium, aluminum is used to improve the corrosion resistance. And so generally lead melting point is 327, and when you have this alloy, it is around 490 degrees centigrade. 327 pure lead can melt at 327 degrees centigrade. Okay, so that's I told you see different design of positive and negative grids. So these are done with the grid caster, and people also use even some polymers even after this to develop the corrosion resistance. So onto this, so this is a metallurgy issue. So metallurgy people work on this different kind of alloys, how to improve the corrosion resistance and reduce the corrosion. Basically, I visited Exide Industries, and what we see actually, they put a lot of batteries in the telecom and the railways. They give 3 years warranty. After exactly 2.5 years, they will see all fails. And then when they bring the cells, you see mostly the positive grid corrosion. The grids have been broken. I'll show you how the grids have broken. The grids breaks actually. Once the grid breaks, then there is no current flow. How it is going to work? So most important thing, that's why the positive, even the grid corrosion is one of the major issue in latest battery industry. Still, if you can make a corrosion resistant grid, you can approach Exide, Amaraja, and you can do marvelous things. You can patent it, you can sell it. So if you look at the active materials, we use lead dioxide. Lead dioxide is a mixture of PB and PBO. Okay, this is lead dioxide. So it's about 85%. Dinyl fiber is expander because these are very hard materials. We use conducting carbon black about 0.1%. Lignin is another expander. We use a nucleating agent because generally for the negative electrode, but for positive we don't use. We use also, I think here also, SCMC, sodium carboxymethyl cellulose is a binder, water-based binder, is used for the as a binder. We use 1.4 specific gravity sulfuric acid, 7%. We use the deionized water around 7.5% as well. So we take all the things, we do the mixture. In the mixture, we put everything and mix them thoroughly, and then we prepare a paste. And sometimes to improve the formation efficiency, I told you 3 cycles it takes. It's a huge time. 3 cycles means you almost 4 or 5 days you have to wait for a lead acid battery to get ready. And you just think of, see, for R&D point of view, doesn't matter. For a commercial point of view, we think of, see, 1 cycle versus 3 cycle. How much amount of current you are spending? How much amount of labor, the manpower, electricity, the other time you are using. See, you can avoid that minimum 4 or 5 days of time if you can increase the formation efficiency. So people, these are the basic reagents, ingredients. People also add many other ingredients to improve the formation efficiency of lead acid batteries. I'll show you some of our papers, may not be results. I'll briefly talk about the papers, and if you are interested, you can download them and can see, or you can ask me, I'll send it. We use red lead also in some positive way. Grid, that's why it is, this is, it looks kind of pink, but sorry, kind of orange color. It becomes black when you form it. Actually, this is form it means when you charge it. So it improves the formation efficiency of lead acid battery. So now already I told you the processes. First, we already prepared the grid. We prepared the paste. then we can prepare the electrodes. We take the grid and coat onto the grid. Your electrode is prepared. Then we do a acid pickling, in 1.1 molar sulfuric acid. Then we do the curing. This is the important stage of battery. Very, very important stage, the curing and drying. It has to be done something like maximum of 65 degrees centigrade. If you go above 65, 70 degrees centigrade, your cell is not going to work at all. It will be very, very hard. So some people go below 60 and some people go around 65 to 70. So in below 60, the paste will be 3BS. It's called 3 PBO, PBS for water. This has basically, this delivers high capacity but less cycle life. But this has a more cycle life, little less capacity. This is formed at greater than 65 degrees, about 65 to 70 degrees centigrade. Your temperature should not go beyond this section. Okay, so 4BS is mostly most of the battery industry, they prefer 4BS generally, so they do the curing at 65 degrees centigrade, and this also takes around 24 hours actually. Okay, so if you get a chance to go to any industry, you will see their chambers like is 7-8 feet trolley can go inside actually. The electrodes will be stacked into the trolley kind of thing, and they put into the humidifier chamber. With it, it's a 95% humidity. You should not have crack. So you think of. So it takes around 48 hours, 24 to 48 hours for the curing action. I'll come to that. What is the importance of curing? Then once the curing is done, then they bring and clean this tag, because it may have some active materials, right? This tag need to be cleaned. Okay, they clean the tag, and the extra access on the top, they can just scrap it. And then, because that is not good for they may come out during assembly or during formation or during in the battery cycling, so that may not be good. So they clean that actually, tag cleaning they do. After that, they bind with the AGM separator or the regular separator, then they put into the container. Now this is, I have a small container. Unfortunately, I don't have a battery here. So, and then they do the activation. Okay, these are the various processes of lead acid battery fabrication. So I told you curing is very, very important. This is because the paste. So if you don't do a good curing, then what will happen? The paste is not going to attach to the grid well. So what will happen during the curing? The 3BS and 4BS crystals are formed. From 4BS, it will form PB or PbO2. Okay, this is very, very important. And during this period, the corrosion layer also form. This is also another important process, the corrosion layer. And also it will form kind of the water will evaporate, and you may have interconnected particles into a porous mass. And also, the paste density will reduce to some extent. That means you will have a pore volume. That's very, very important, for particularly lead acid battery kind actually. So the lead acid battery, so you need to have because the ions like sulfate ions has to go on interconnect, correct? So during this period actually, so you should have good porosity also. So you see here, if the paste is like this, then what happens during a cure? They have interconnected particles, and when you form it, I'm going to calm it. When you charge it, it will form this kind of particles actually. So you will have now interconnected particles when you form it. You see, initially they don't have interconnected particles either. So this is we have seen by SEM as well, scanning electron microscopy as well. So it basically, if you want to prepare, you can ask me, sir, how much amount of electrolyte, how much amount of active mass I should take. So in basically what we have seen, around 8 to 10 milligram gram of material gives you 1 ampere hour. This is around, if you see, this is around 30 grams. So this will give you 3 ampere hour. Okay, so approximately, you see this is approximate calculation, and you need 8 to 10, at least 10 ml of electrolyte for ampere hour. For ampere hour, 8 to 10 ml. 8 to 10 ml. So in a small cell, maybe 10 ml. In a like whatever you see in the BRL cells, BRL batteries, that is 10 ml. Sorry, 8 ml. BRL cells 8 ml. Plotted maybe like this. It can go to 11 to 12. Okay, this is one of the important thing. So efficiency, I was telling, the efficiency of latest battery. It's not that all the materials are utilized for electrochemical reaction. Only you see, instead of 240. I told you around 200 to 240 milliampere per gram of lead oxide. Now, but we get around 100 or 220. So it's around 40 to 50% efficiency. So accordingly, if you see if it is 50% efficiency, you see around 10 to 11 gram for PbO2 and 10 gram for Pb, and around 13 ml of sulfuric acid is required for the latest battery fabrication. Okay, so now we learned about now we have electrodes, now we have electrolyte, now we have to form it. We have to make cell. We stack them in the industry, with the help of separator, and put them into the container. Correct. So generally, two kinds of formation is done: tank formation once the electrode is done after curing, or container formation. Whatever batteries you see, the BRL batteries, they are done container formation in situ. They have not done. Their formation is not done outside. In many cases, many plotted system, they do tank formation. What they do actually, they take 200, 300, or 500 electrodes, and they take counter electrodes, and in 1.1 molar sulfuric acid, they do the formation. Okay, so they do the formation, do the charging. This for a long time, maybe 48 hours, 100 hours, and then full charge it. Then that is flow rate, and that's also very good actually. We have seen. And as a container formation, so what they do, I'll come to the next slide. So they do a charging also for charging in the in situ. So here electrodes are done in a big tank. Here the stacks, the electrodes, positive, negative electrode together, put into the stack, and done the filling the electrolyte, and then soaking, and then formation done. Here it is separately. So the only plates are arranged in a tank and done the formation. And then when the formation is done, they stored, and whenever it is required, they assemble it, and then again they charge it. Just one cycle it may take to do the get a full cycle. So then you get full capacity. Here you may need 2 to 3 cycles to get the full capacity in the container formation. So one important thing, once you put the electrolyte, 1.25 or 1.26 or 1.24 specific gravity sulfuric acid. So what you see actually, so as soon as you put sulfuric acid, you will have a lot of heat evolved at the positive and negative electrode. Lot of heat is generated at the positive and negative electrode. I told you the temperature should not go beyond 65 degrees centigrade. Okay, so what they do actually, they put in water. Okay, all the cells they put in water, because if the temperature goes above 60 degrees centigrade, 65 degrees centigrade, there is a possibility of a change in active material to a different composition. So that's also very important. During formation and soaking, the soaking and formation, the temperature battery temperature should be taken into account. So we do the formation. So generally, those who are interested, if we can see 1 to 3 milliamp per centimeter square current is required for the lead acid cell. So this is, if it is 35 centimeter square, you see here this is 35. We put around 100 milliamps. Correct? Around 100 milliamp for 35 centimeter square, minimum around 100 milliamp current. So for accelerator formation, you can go even 5 times, 3 to 4 to 5 times for more than of this actually for accelerator formation. Generally, people go with 1:3. Lead acid battery is a slow battery. It works very well if you do a charge discharge at C/10 rate. That means 10-hour charge, 10-hour discharge. You will get full capacity. If you do a 5 C/5 rate, like 5-hour charge and 5-hour discharge, you may get 90% capacity. But it's not the same thing in the lithium-ion cell. If you take a lithium iron phosphate, 1 C rate, whatever capacity you get, C/10 rate, almost the same capacity. Whereas here in the lead acid cell, in 1 C rate, you may get 75 to 80% of the capacity only. That means 25% is lost. So again, when you do a charging, the voltage, see, this is a maximum 2.6 volt per cell you should keep it. And the temperature, as I told you, it should be maintained between 25 to 55 degrees centigrade. Okay, and always so these are the important parameters. So the current, voltage, temperature, these are three important parameters that helps us to make better batteries. So how do you do the formation? You can go for the constant voltage charging. You can hold at 2.6 volt or 2.45 volt, and then what will happen? Your currents will be very high initially, then it will reduce. I don't suggest this CP charging. There is another one my all our students do, CC charging, constant current charging till a particular voltage is reached. In lead-acid battery industry, generally CCCV charging is followed. Even I used to do in my postdoc times or PhD times, I used to do CCCV charging to get full capacity. So what is that CCCV charging? So suppose I have voltage of 2.6 volt. This is a 2.5 volt. The now current is increasing. So now current, constant current. This is the constant current. The voltage is increasing. After it reaches 2.5 volt, the current will reduce. And this is the float charging. This will be, I'll be doing something like 12 hours to 48 hours. So it will be, this is the charging generally followed in industry, CCCV charging. Okay, you go CC and CV charging, so that to get maximum capacity. So these are the three different ways of charging: constant voltage, constant current, and constant voltage, which is your charge. Generally, your inverters are charged at something like 2.3 volt per cell into 6, so which is 13.2. So it's always float at 13.2 volt. So very small amount of current will be passing into the cell. So now we have made the cells and batteries. Suppose you want to know about the electrochemical oxidation reduction processes, whether it is my cell is reversible or not. We do, first we make a small cell like this. Industry we make a 10 into 10 or 12 into 12, or even kind of 1 feet, 2 feet into 1 feet, like big electrodes. But in a lab, we don't go beyond that 7 into 5 centimeter square area electrodes, because that's convenient for us to assemble and easy to use and with our systems. So first, what we do actually, we do I forgot actually. First, we do a impedance actually to understand what is our electrode resistance, what is our ohmic resistance, because these are very insulating in nature. And we fortunately we have a good electrolyte like a aqueous sulfuric acid. Okay, it has a good conductivity. So if you see, the electrolyte resistance should be as less as possible. So we do a impedance at two different frequencies. So we get electrode resistance, electrolyte resistance, and charge transfer resistance. Other things we get. Not to worry at all anything. So even without this instrument also, from the voltage profile in the past, we used to calculate the ohmic resistance. So for example, I'll just tell you if I have volts. So you see, just a second, I have yes. So basically the OCB will be here. This is the voltage profile. Suppose the lead-acid battery, then after, as soon as you put the current load, you will have a drop, correct? Where the fast drop happens actually, kind of that. So the voltage, the current, then I equals to V by R. You can easily calculate the resistance actually. This is approximate, you can easily get the I equals to V by R without impedance measurement. You can get, and this should come for lead-acid battery. It should come milliohms. Whereas in aqueous electrolytes, non-aqueous electrolytes, it will come in ohms. So it should come less than even 50 milliohm. Okay, and for the battery industries, would be even still lesser because their assembly is much better. Then we do a cycle voltammetry to understand the redox processes, where the oxidation is happening, where the reduction is happening, and so on. So if you see, I won't go into details. If those who are interested can see, cycle voltammetry is performed to understand the oxidation reduction processes. So EPA minus EPC. So this is a IPA. This is the current, anodic current, cathodic current. The IPA by IPC pass to 1, then it's completely reversible. And EPA, the voltage you see here, this is the cathodic, this is the anodic voltage. So if see this is the anodic voltage minus cathodic voltage. It is APA minus EPC. If it is a 59 millivolt, you tell 59 millivolt by N. N is the number of electron transport. If it is one, it is one electron process. If it is 30 millivolt or 29 millivolt, you tell it is a two electron process. So many people also calculate the electrochemical active area. You can calculate the charge and many other things actually. Okay, even you can calculate the diffusion current as well. So I don't want to go details. So you can understand what the oxidation reduction happening, and accordingly you can also do a cutoff voltage. So after the oxidation you can stop the reaction. Maybe sometimes you can see it will be like sorry. So after this position, you can stop the reaction, correct? That means shows that there is no more charge is getting accepted by the cell. So you can stop the reaction. That gives you the cutoff voltage of the cell. Okay. So these are the things we do. We do a charge discharge actually. The another important thing is charge discharge. Okay. This is very, very important. This gives you the voltage profile. The charge discharge gives you the voltage. When you discharge at different C rates. I told you one C refers to the capacity in 1 hour. C by 10 is the 10-hour charge discharge. C by 5 is the 5-hour charge discharge. C by 20 is the 20-hour charge discharge. See the voltage profile. See, if you are getting 25 hours, it is this is C by 25 rate. C by this is not correct. This is not correct. Who has plotted? C by 10 means it should be 10 hours. This is C by 20. This is the C by 15. No, I don't know. Who was this is not correct. So what it does actually, it different currents are done. C by 10 means it should come 10 hours, and this is C by 25. Correct. So as I told you, from the Picot plot, you can calculate the current. So exactly, see, once you do 1 C rate, once you do C by 20 rate, exactly 20 hours you should get, and 1 hour exactly you should get. Once you get, then you plot it, you'll get a straight line, and then you can calculate the current at a particular C rate. So what it gives, you see here, it gives us the voltage profile. At this voltage, the nominal cell voltage you can see here is around 2.1 volt or something. This is the region where it can operate. And this shows you this is the cutoff voltage. That's why I told you in the CV then. So see, after this is the polarization is complete. You don't have to discharge it. Similarly, while charge it like this. So that means you don't have to go beyond this region. Okay. So this charge discharge profile will also help you to do the not only say I into T will give you the capacity. So you can measure the capacity from here, and also so this also from the CB you can know what is the cutoff voltages. Here also we can determine the cutoff voltages. You don't have to go actually beyond this voltage. You don't get any capacity. But in the laboratory we try to do to get more capacity. And so this is how we do a charge discharge, we do a CB, we do a impedance, and also we do cycle life. So at a particular C rate, like suppose 5-hour charge and discharge rate, we try to do that, or 1 hour charge discharge, we do a cycling. So how many cycles is stable, whether it is 1,000 times or 500 times at a particular C rate. So that gives you the life of the battery. So one discharge equals to 1 cycle. So we do the charge discharge cycling, then we get for C by 5 rate, that means per day you can do about 2 cycles. That means 300 cycles will take around 130 140 days to complete at C by 5 rate. Okay, so at 1 C rate per day you can get 12 cycles. That means per month you can do something like 360 cycles in a month. Correct? Yes. So already I told you different C rates also you can do 1 C rate, 2 C rate, and different currents you can do. So that for different application you will get different voltage profiles. Accordingly, you can decide which application will be good and what application, like what currents you can pass actually based on the voltage profile and based on the C rate. So next 10-15 minutes maybe I'll be talking about what are the factors that affect the battery performance, and already I told you what are the limitations of latest battery. That's I'm going to talk. See, always you think free energy of all electrochemical reactions should convert into electrical energy, but it doesn't happen. So you see a drop in voltage. correct? You see a drop in voltage. This is because of a lot of surface chemical reaction. The concentration depends between the reactant and the product and the ohmic resistances. Okay. If you want more details, you read here. So ohmic resistance are basically, let me tell you about the ohmic resistance. You should know at least. See, no, you see here, this tag I connected here. And you see, I connected to here actually with the soldering. The contact resistance between here to here. And this one I'm putting a crocodile clip to the instrument. The instrument wire to the instrument, like to the instrument, also there is a contact resistance. Now you see here, I'm putting active material here. So now current is passing here and then active material here. So the current collector to the active material, there is a contact resistance. Even in the active material, you use lot of additives also. Okay, they are maybe non-conducting even. That also contributes some resistance. You have pores. The electrolyte is filled in the pores. That's the electrolyte resistance. Pore resistance. All this contributes to the ohmic resistance. So the ohmic resistance should be reduced. For high rate application, the ohmic resistance should be reduced it should be as small as possible. So this is very important. The engineering part of this battery is very, very important for good performance of good battery life actually. So how you analyze this latest batteries? So once you see a failure in the latest battery, so you need to disassemble. No other way. So you need to So initially maybe you can check what is the voltage. If it is not 12 volt, suppose it is 10 volt, that means one cell has gone. If it is 8 volt, that means the 2 cells has gone. When you charge it, you will see the difference. It may not be going beyond that voltage actually. It will be 8.2, 8.3. That means some cells have been gone. Until unless you cut open, because the cells are inside, only the 2 terminals have come on the lead on the cover. Until unless you cut open the lead, you won't know like which cell is not working. So then you can check the voltage. Once you cut upon, you cannot reuse it, but you will understand which cell has got bad. Then accordingly, you can take out the cell and you can just check what has happened, whether grid corrosion has happened or the sulfation has happened or what has happened. That you can see that. And these things you can understand by a lot of surface techniques. We have XRD, X-ray diffraction, that can help you to understand the structure of the material, whether it is a PbO2 or it's completely PbSO4. That you can find out. Whether the particle size has increased. Now, initially I took nanoparticle. Does it forms a bigger particle? Because lead sulfate is very big. If it bigger particle has formed, they may not allow the ions to move. Lead sulfate is insulated. So these things you can understand by XRD, SEM, TM, even XPS. XPS is a surface technique you can understand. And also during operation of the cell, you can do impedance, first cycle, 100 cycle, 500 cycle, 1000 cycle, so that you will know that increase in impedance. If my impedance is increasing drastically, that means my cell may be going to fall. Capacity is going to fall. My life of the battery is going to fall. So like this, you can understand many aspects. So if you see the latest battery, so initially you see they look like this, the negative electrode, right? So after a few few hundred cycles, so you see this kind of things happen. This is because of lead sulfate. This is the hard sulfation. So if this happens, so the electrons are not going to flow and ions are not going to move. It's a very, very hard sulfate. So I don't want to go details. So another thing, what happens actually, so at slow rates, so what will happen if you are doing C by 20 rate, 20-hour charge or 10-hour charge discharge, many electrons or ions, you have enough time for the electrons to move and ions to flow. But what happens when you go at high rates of charge, like suppose 1C, 10C, then what happens? You have sulfate on the surface or the surface. Then what will happen? It doesn't allow the sulfate ions to move or electrons to flow out, because it cannot go interior of the plate with the small time actually. So then what happens? This performance becomes zero. Suppose you are using for electric vehicle application is not going to work at high rates, like when you put brake, not going to work at all. This is called high rates of partial state of charge, HRPSUC, high rates partial state of charge. So what happens actually before cycling, they are all nanomaterial, and after cycling, you see like big crystals of lead sulfate have formed. This has been analyzed by XRD, SCM, and other techniques as well. So this is the main failure of a legacy battery. So so that's how you see the difference between the electric. You can easily understand when you cut upon the cells actually. So this even I have seen in the industry. So this is the major problem of lead acid battery. So how to reduce the sulfation? So it has been seen that carbon additives improve the sulfation. You can use carbon nanofiber, you can use graphene, graphite, few percent. We have we have added. Let me show you. We have done a lot of work on how to improve the active material utilization. See, we have done in situ work like how to improve the formation efficiency from 3 cycles to 1 cycle. How to reduce sulfation. That means if one sulfation is reduced, that means it improves the HRPSSC application. Our goal is to reduce sulfation and improve the formation efficiency and improve the active material utilization. So we have developed, one of our student, Dr. Naresh, he worked in this material and he developed titanium dioxide graphene oxide as additive for the latest battery. Also, he developed some electrolyte additives for the latest battery. Boron dope graphene nanosheets are the negative electrode additive to latest batteries. Carbon coated SN2 as negative electrode additive to the latest battery. So what happens actually? Why with the metal oxides? Carbon improves the conductivity, but what happens at the high voltages? So what will happen? There will be possibility of carbon dioxide evolution. So we use a small amount. So it is not used in the positive electrode. It is only used in the negative electrode. If positive electrode is used, then what will happen? Carbon reacts with oxygen to form carbon dioxide. We don't use at the positive electrode. We use at the negative electrode. So metal oxides, carbon with metal oxide improve the reduction of hydrogen emission and improve the charge acceptance. That's we have seen actually. Even polymer coating onto the negative plate also improve the performance. So he has also developed corrosion resistant polypyrrole grid for this addressing all the issues of lead acid battery. The thesis was like a development of high performance lead acid battery through electrode and electrolyte additives. You can do still lot of work is done required to improve the performance of lead acid battery. So sulfate is a major issue in lead acid battery. I told you nanomaterials become, you see here micro. See, this has become 5 or 10 micron. This is even if it is a 50 micron or 50 nanometer particle, it become, see, you see the in real, it becomes several micrometers. Okay, it is just in 500 cycle. This is conic electron micrograph. That means you have a big growth of the particle. So how to improve the conductivity of the paste? Most importantly, what I talk here, to improve the conductivity of the paste so that you have, it's not that bigger lead sulfates are not producing. Also happening, maybe instead of 5 cycle, it goes 1000 cycle. You can do also same thing. Can I improve from 1000 cycle to 2000 cycles with different additives? This, this is a small insight. So what I was telling, like additives to the active mass improve the performance. Now I'll talk about, so I didn't change the electrode configuration. I use same lead acid battery electrode, negative electrode of the lead acid battery. I use as such and added some additives. Just even if you see here, if you see all this paper, less than 1% additive, even 0.1%, 0.25% kind of additive has been added to this electrode to improve the performance. But still, the sulfate issue is not 100% removed. So to overcome these issues, lead carbon hybrid ultra capacitors have come up. So what is done actually? The negative electrode of the lead acid battery is completely removed, and you can use. So So this is the lead-acid battery. You see, the negative electrode is completely removed, and you put a carbon electrode of the capacitor. So it is no more a lead-acid battery. It's called lead carbon ultra capacitor. This is one way you can improve completely. You can eliminate the lead sulfate formation. This is one way. The second way is that you can have the same lead-acid battery. You see, lead electrode, lead acid electron, and you can use a carbon electrode. That is called, see, 3 electrodes in a cell. You might not have seen 3 electrodes in the cell other than the reference electrode. This is, I'm telling, real electrodes. This is called ultra battery, which was developed by CSR Australia. I'll speak for a minute actually. So let's talk about lead carbon ultra capacitors. See, lead carbon ultra capacitors. So you have lead oxide cathode and carbon anode. But as you see here, we have a lot of mass here in the cathode. So the anode need to be optimized. Carbon electrode may not have that much mass. So this has to be done in a different way. So the same way it doesn't work. Lead acid, there should be very, very thin electrode. So you see here, this is the same like your lead-acid battery electrode reaction, PbSO put to PbO2, and then you have this is the carbon, okay, hydrogen adsorption on the surface of the double layer, the carbon layer, correct? That the electrode interface you have an adsorption that gives around 2 volt, little less than the lead-acid battery voltage, but it works very well. Okay, so what I want to tell you, like you can have a different configuration. This area is very, very new, and you can work a lot actually. People work, lot of porous carbons. Ultra capacitor has been significantly studied. The same electrode of ultra capacitor can be used in lead carbon batteries. Lead carbon. So this is the ultra capacitor electrode. I don't want to go details. If you know carbons. Now from India, you see hundreds of papers are published even every month or quarterly on carbon electrodes. Many university colleges and IITs or IIC everywhere they produce a lot of carbon electrodes for supercapacitor. The same supercapacitor electrode can be used at the negative electrode of lead-acid battery. Okay, so generally high surface area around 1500 meters square per gram used as electrode material for the lead carbon batteries. Okay, so you can have even hard carbons. You can have activated carbons like which has a high surface area. I don't want to go details of supercapacitors. They have 3 different mechanisms of how they work. So these are the secondary things. I don't want to go details. This is one way where we can improve the performance of lead-acid battery. So I don't want to go details of this. So the most challenging part of lead carbon hybrid ultra capacity is that, again, you need to have lightweight grids for both electrodes. Generally, we try to use graphite electrodes and lead sheet at the present for the positive electrode. Lead is activated the similar way, but we are trying to have electron deposition of PbO2. Okay, so you can already, as I told you, these are all supercapacitor materials explored extensively in the literature. Even metal oxide pseudocapacitor materials also have been extensively studied. And also another important thing is that here lead oxide, how to make a thin long life lead oxide electrode for supercapacitor. This is now no more battery, this is a supercapacitor. And we are using almost same electrolyte concentration, 4.5 molar. So the capacitance could be significantly improved than the regular capacitors. So we have done several works. You can see the student Sadanand, he has been doing significantly in this area. So he has developed boron nitrogen doped porous carbons, from bio waste as a negative electrode. Nitrogen doped carbon for polyphenol, and this. The next one I want to talk about ultra battery. I told you we are not changing the configuration of lead-acid battery. We are putting a capacitor electrode. So you see here PbO2. So in the capacitor, this is the lead-acid battery. This is the lead carbon capacitor. Now I'm going to remove this. Okay, or just adding the carbon electrode here. Okay, this is called ultra battery. But the problem is, this is the problem. So this is when the problem is that the current sharing between the capacitor electrode and negative electrode of lead acid battery during early stage of discharge. If you can make a combination, because you see here the voltage profile here. Okay, so how to make the capacitor electrode to share the current of with the negative electrode of lead acid battery during early stage of charge, that's the discharge. That's very important. Also, what happened, there is a gassing reaction may occur at the capacitor electrode at the end of charging, so that may also cause a dry out of the battery. These things should be taken into account to make ultra batteries, so lead carbon and ultra batteries. Okay, so I told you about corrosion of the positive electrode. Corrosion is another inherent property. You know, I told you exide or any battery industry you go, after a few years of use, their electrodes become this. Then how the current will pass? Current cannot pass. So if this terminals goes away, how the current will be going to pass to the electrode? So that's how it is like, this is another major problem in legacy battery. So people try to see like this. This is our own electrode. This is the small electrode what student prepared, and you see the configuration. Very strange. After 500 cycles, it's become like this, completely corroded. So the activator is not utilized and it not doesn't work. Okay, so the grid corrosion must be protected. This is another area. My students have developed some corrosion protected grids with the polymer coatings, but still a lot of work need to be done. It can be, the alloys can be improved and so on actually. So this is another metallurgy or a little bit of chemistry issues that can be developed, corrosion protected lead grids for the lead acid batteries. Okay, that can be done. So people use a lot of additives to the alloy to improve the corrosion resistance so that its life becomes more. This is I told you conductive polymer coating to the polymer. This thing also helps, and a lot of additives people use. Silver generally. Some people use tellurium, selenium. All the things are there, but mostly lead, calcium, tin, aluminum alloys used. It's okay, but still not up to the mark. If you can have a good corrosion resistant grade along with the reduced sulfation, it can improve the life of the battery. And water loss is another issue. I already told you oxygen evolution and hydrogen evolution in the lead acid battery can cause together water loss, or oxygen hydrogen evolution, grid corrosion also causes water loss. So in the past, we developed platinum Syria catalyst to reduce to do a oxygen and hydrogen combination inside the cell. And again, this has to be done in a systematic way to combine the hydrogen and oxygen, because in the VRLS cell only few little of hydrogen oxygen involved, only when you go to the high voltages. So this is another area you can also focus. Those who are working on catalyst, they can work on like how we can work catalyst for the hydrogen and oxygen recombination inside the cell of lead acid battery. Okay, we had also different design of catalyst plug for putting into the cell even. So we have tested also. We have published a couple of papers. This was maybe during my early career of my PhD. This is my senior colleague, and in 2001 even this was published. And then people use also a lot of multi-wall carbon nanotubes, single-wall carbon nanotubes, graphene to reduce, or metal oxides. Metal oxides generally used to, thus I told you, SNO2 or TiO2, we used to reduce the gas evolution, the hydrogen evolution. And the self-discharge is another issue. Already I explained. I don't want to go details. This happens, even in open circuit. Again, so mostly people work how to improve the conductivity of the paste so that the cell reduce the reactivity, oxygen evolution and hydrogen evolution. Basically, oxygen evolution. How to reduce oxygen evolution? That also people have been working. Acid stratification. So this is the orientation. Like this is an engineering issue. How we can make that acid concentration should be very uniform. So the last one I want to tell you about thermal runaway. This is another issue in lead acid battery. So as I told you, oxygen reduction happens at the negative electrode. Another important thing happens at the Joule heat. So when you have a sulfation is happening at the electrode, so when current passing to the conductor, it makes heating. That's called your Joule effect or Joule heating. Correct? So the temperature of the cell rises drastically. Some cells it's like 60 degrees, and some cells it can go to 100 degrees centigrade. I'll show you Professor Pavlov. So I have seen his lab. You see, the lead acid battery become like this. and it's very dangerous. Then what will happen? It may burst, and acid spillage can happen. And of course, it may not cause severe injury, but but it can cause explosion. I remember once we were testing a battery, and the battery went even 3 feet, like 5 feet high, and then fall on the down. It can happen even. I remember those days during PhD. This thermal runaway in lead-acid battery can be avoided. Okay. So another important area, recycling. Of course, recycling lead-acid battery is 100% recycling. How from the suppose from the separator, whether the separator is 100% recyclable. From the separator, can you make a value-added product? Anyway, the containers are recyclable. Lead is recyclable. Even there are some lead waste. Can you use them and can make some valuable products? So that's another area where you can focus. So with this, I just want to tell you today I briefly talked about lead-acid battery, gave the fundamental insight to the lead-acid battery, the electrochemical reaction, the schematic of lead-acid cell. I talk about what are the issues associated with the lead-acid cell, like oxygen evolution, hydrogen evolution, corrosion, then the sulfation, the corrosion, the specific gravity change, the then stratification, all these issues. These issues can be mitigated by various items that I showed you. And most importantly, I told you also how we can fabricate these electrodes in the lab. If you have a collaboration with the industry, you can do marvelously. Any industry, if you are interested, you have some idea, they will be happy to help you actually. So you can make today we discuss about how we can make these electrodes, and starting from the grid casting to the slurry to the paste preparation to the coating to the curing, then tap cleaning, then to assembly. Then we talk about formation, how we can test them, and how what are the issues associated with the material, like how we can address these issues. We talk all about actually. And I hope I try to give one insight to you on the area of latest batteries. And still, you have a lot of scope in this area to work with the latest battery. Latest battery won't die in India. Let me, you will tell me like still, because you see, you talk about lithium-ion battery. Neither lithium resources or cobalt resources are available in India, and cobalt resources is only available in only Congo. Okay, and this is a political center tension country. And think of all the things, now we are fine. Maybe if everybody drives an electric vehicle, question comes, can we have enough lithium and cobalt or nickel? Okay, so, and these batteries are readily available, everywhere in the world. These batteries won't die, even, won't die in the world. Still will be keep using, because most important thing is that 100%, 98% recyclable, low cost. I won't bother about cost now, because lithium ion battery also becoming cheap, is abundant, available, and so it can be easily available. That's a very, very important thing, for Indian perspective, if you see. Okay, so with this, I'll conclude. Before concluding, I just wanted to show you one small video which even on the which recently we developed on dual carbon batteries actually. So where in the lithium ion cell we are replacing both electrodes with carbon electrodes, and what happens? The electrolyte ions interconnect above 4.5 volt of where the lithium battery doesn't operate. Above that voltage, the electrolyte intercalates into the cathode and anode. The anions like PF6.
Where is standing? Just like that?
So, hello.
So, yeah, we can see. Please go ahead.
The electrolytes ions can intercollect and can give you the voltage of, like, the voltage of the cell around 5 volt and the operating voltage around 4.65 volt. And a lot of work need to be done in this area. This is the next generation battery. Even you can tell it can be a next generation battery, and this can be about 25% cheaper than the currently available lithium-ion batteries. And a lot of work. This is a very beginning. A lot of work need to be done, and it's 100% recyclable and very easy because both the material, both the cathodes and anodes contains carbon. Okay, so I'll show you this video in a minute, and this has been broadcasted yesterday in Rajya Sabha TV. You can see them in the YouTube as well. So this work, initiated here, and then this is my collaborators, Chris and NMRL funded this project.
So we are not able to hear your voice here in this video, but we can see the video.
You are not able to listen?
Yes.
Able to listen or listen?
We are not able to listen. We can see the video.
Okay. Anyway, maybe I'll just because
or you may. I think this is already in. You can give me the URL for this video. I will share with the participants.
Yeah. It's I can share. Yes.
That's
you can. Is it audible? So with this, I would like to thank all my collaborators and the funding agencies for their continuous support, and my students, who supported, because of whom today I am here today. So finally, I thank all of you for your kind attention and welcome for any questions.
okay. Thank you, Dr. Mata. We have some questions which students have typed already. I'll just read out some questions. The first question is by Bhavesh. He asks, which battery has high capacity for solar energy?
Capacity, if you see currently, it is lithium ion, correct? So it is lithium ion batteries.
Okay.
But
the next question is by Brijesh Pandey. He asks, which type of battery will be preferred for a online 10 kVA UPS?
See, if you have access to lithium-ion battery, I'll suggest, and if you don't have, you can, make it. Like you don't have money constant and other things, you can buy a lithium-ion battery. It's available. I can share with you some details about the manufacturers around Hyderabad. Also, there are many industries. They get batteries from China and they make stock and sell it for all inverters and electric vehicles as well. And as always, latest battery it can sustain also very well. So both are
The next
fine.
question is by yeah, please continue. Please continue. Sorry.
Yeah, both are fine. If you don't have a money constraint, you can go with lithium. Lead acid is also fine. See the manufacturers. See, you have to see the UPS. The UPS should support the battery. You should able to charge and discharge. See now all the inverters, whatever you see, mostly with the lead acid battery. Now I believe the manufacturers are now aligning towards the lithium ion battery as well. Correct. So the UPS, the inverter should able to charge your lithium ion cell. If it doesn't charge, then you may not get a good capacity. And maybe I think in a few years' time that those problems will be solved, I believe, because mostly the inverters are aligned with the latest battery at the present. I can tell you.
The next question is by Anuj Raturi, Assistant Professor Anuj Raturi. He asks, would you please enlighten on charging cycles of batteries? How can it be improved?
Charging, see, if you talk about latest battery, I showed you a lot of additives, correct? So the additives help to improve the charge formation efficiency, antimaterial utilization, and the charge efficiency. And charge acceptance, basically what you talk about. The additives help to improve because conductivity, you have to improve the conductivity of the paste. Then only you can improve the charge efficiency.
The next question is by Harshita Singh. She asks, sir, like you said, you work on sodium ion and lithium ion battery. We know lithium has limited source, so we can't explore it more. And sodium is in abundance. So can explore it to great extent, but still efficiency of sodium battery is set to lack a decade. So how can we increase efficiency if you talk about sodium ion battery?
See, always nowhere the sodium ion battery can be compared to lithium ion battery. No other battery system can be compared to lithium ion batteries at the present because you see the performance metrics are very high, power, energy, all are very good compared to other battery systems. Correct. So you talk about sodium. So first, if you see the capacity of the cathodes and anodes, everything is much lower than the capacity of lithium and battery materials. But still, it is worth studying this material. Today it has not come to reality. Maybe it will come in decade in the next 5 years or 10 years time, because the sodium materials are abundant in nature. You can talk about, suppose, I understand, even lithium iron phosphate, you have 1 mole of lithium. Or sodium, sodium olivines, like sodium olivine compounds, if you see, we have sodium. So sodium is abundant. So it's worth studying the sodium and battery material, but it cannot be used the way lithium and battery used in a variety of applications like EVs. Time will say all the things, but sodium and batteries are good for grid application. That's I can say at the present. But this is when you see in the 10 years like and compared to 30 years of lithium ion, they followed just simply the lithium ion chemistry and did the research, and significant improvement have been done, and we are able to achieve 100 million watt hour per kilogram. Whereas lithium ion, of course, it is more than 200 watt hour per kilogram. With the breakthrough in these materials, I believe one day we'll have also sodium ion batteries, better sodium ion batteries. Who knows? Right? So it's worth similarly solid state batteries. See, you just think of 5 years before, there was not a single company on solid state batteries. There are now tens of companies or hundreds of companies on solid state batteries all over the world. This is because that is the emerging technology is coming up. They know, see, the coating process initially was expensive. Now they have developed coating processes where it is. So I believe, with time, with the technology evolution, this is going to change and we have a better even sodium ion batteries. It cannot replace the lithium ion batteries in the terms of energy density, but it can have some impact on the battery technology.
Okay. The next question is by Kundu, S. Kundu. He asks, what is special about tall tubular lead acid battery as it has got better lifetime and better C rating?
tall tubular is the grid, the design itself is so the current you can pass high currents. Okay, and the life is much higher compared to this systems actually. These are very thin grids. The grid corrosion is somewhat lesser over there. Here grid corrosion is much higher. What I showed you actually. So tall tubular cells always the design is different. So that's why their life is much better than the currently available this VRLS systems.
Okay. Next question is by Harshita Singh again. She asks, we know graphene has many advantages over graphite as an electrode. Still, we mainly concentrate on graphite. Why is it so?
So, say graphene is you think, no, we are not able to make a good quality graphenes, right? That's why it's expensive. Even though everybody knows, you see, any college, university, everybody knows how to prepare
Lost. We have lost you, Dr. Martha. We lost the connection. We're not able to hear you.
Hello?
Yeah, now we can hear you, please.
Yeah, my other computer got disconnected.
I see.
Okay, so
we didn't hear your answer. Can you please answer?
So regarding graphite,
graphene.
see, as I told you, with time, with technology evolution, if graphenes are available with low cost like graphite, we can use them. There is no doubt in that. We know how to prepare graphene, but still the process is not very abundant. Like we are not able to make a good quality graphenes, correct? Still, we are lacking behind. Even though we tell graphene, this is not graphene, this is reduced graphene oxide. And you think of the amount of graphene present over there is very less. So that's why we rely on the mostly graphite or graphene like this reduced graphene oxide. Once with that's I've told you this is sodium ion battery, graphene. These are the with technology evolution. I believe in few years time these things this won't be a constant, and I believe with this technology evolution we'll have a better graphenes. Graphenes also will be cheap, and sodium ion battery also. Now you see sodium ion batteries are not if it has come, it is the similar price of lithium ion or even more because the technology is same. The material, the technology is same. So I believe with the technology evolution, these materials will be readily available and we can use them in the batteries actually. And again, so graphite versus graphene, you see graphite if you use maybe 4% or 1%, 2% can be used. When you graphene you use less percent can also work well. Even single wall carbon nanotube, if you can prepare, you can use less percentage. And how to make it feasible? This is a commercial feasibility. The commercially is not available. That's why we are not very whatever is available. Why still latest battery exist? This because of availability. So it should be available. It should be readily available, and we should be able to make it easily. If you are able to make a graphenes easily, then it will be. We can all use instead of graphite, we can use graphenes. But again,
the final question is,
this may be additive for this is the additive purpose. If you want for the other purpose like lithium ion battery, that's a different story. Maybe our Dr. Praveen can answer tomorrow those questions.
The final question is, can these be recycled? I think is with respect to graphene. Next question, can these be recycled? The graphene based electrodes?
Yes, I told you dual carbon is 100% recycled. Why cannot be recycled? It can be recycled. See, graphite intercalates to, so you see lithium or sulfate intercalates to the graphite, and you can have better reduced graphenes. Actually, this is the one way of preparing graphenes even. So you get better graphenes, due to intercalation.
This is one way of process of preparing graphene. So you have a better graphenes actually. This is a better way. You know, recycling lithium and batteries, graphite electrodes, you can easily prepare graphene because already lithium or PF6 is intercalated into the already intercalated into the graphite layers. So you have a good exfoliation of graphite and you do the reduction, you get a very good graphenes actually compared to your graphite in the normal process. We have been doing.
I think we are out with the questions, whatever was asked. If anyone has any question, they may just raise, unmute and speak. I'll just wait for a couple of minutes and then we can close the session after this. Okay, Dr. Mata. Thank you for your energetic session. The talk was very energetic and information is well received by everybody. We would also upload this video in the YouTube channel. So please, in case you want to have any doubts, you may always write back to Dr. Mata. He'll be happy to.
Anytime. You know, I have given my phone number even. You know, better I prefer to have an email instead of a phone call. Okay, I'll answer to your question, and I can share all literatures. It's all available also, and there is lot of. I want to tell you, you know, if you want to collaborate with us, you have some ideas. You know, even you yourself can get funding to do the research even. No, now a lot of ACRB programs, GST programs are available where you know a IIT and you know other organizations like colleges and university can combine write the proposal. You can write a proposal and with the help of us, and you will be compiling with the help of us, and that can be also possible. There are many such proposals, and early career awards and other things are also available. So please, you know, I request, you know, I have been to many colleges in unfortunately last 1 year I have not been. So I interact with many college lecturers and all things. So but I feel actually you should start doing, you know, it needs a little bit of your time, you know, more than your teaching. We understand that you have been loaded with the teaching, but still, you know, this is a good way to explore yourself and keep get into the research. You know, this is a very good. It's really important for you to grow further and you know in your academic career. This will really helpful for you and to get connected with the people even. You know, so this is a very not only latest battery, lithium ion battery, sodium ion battery, other battery chemistry, and you know you can do that. You know, this doesn't